Assalamu alaikum warahmatullahi wabarakatuh. In this video, we'll talk about calculating the equilibrium concentrations and pressure by using the ICE table. So what is the meaning of ICE table? So first we have three letters here. What is the meaning of these three letters? The first one is called the initial one. So we're talking about the initial concentration or the initial pressure. Okay, and then C, which is the change. So we'll check what is the changes will happen for all the substance inside the reaction. And the last letter, which is the equilibrium concentration or the equilibrium pressure. So what we are going to do, we're going to start with the initial one, see what are the changes will happen for this initial, and this will give us the equilibrium or the final concentration and the pressure at equilibrium. Let's start with example here. For this reaction, formula reaction, we have A plus B will give or produce 2C. Okay, if we started with 2 moles or 2 molar, sorry, of A and 3 molars of B. So this is the concentration of A, which is equal to 2 molar, and the concentration of B, which is equal to 3 molar. And this what we started with, so this one is the initial concentration for both. And at equilibrium, so we have something at equilibrium here, the concentration of C. So this is the concentration at equilibrium for C to be equals to 2 molar. So we have the initial part and we have at equilibrium only one information. Okay, so we need to find the other concentration for, or the concentration for other substances at equilibrium, which is the concentration of A and the concentration of B. So how to find the concentration of A and B? So we need to find it through the ratio between the moles from the equation here. And this will be done easily by the ICE table. So first, to do the ICE table, I will just start by writing the equation. Or you can just write the substances that you have. Okay, so for this one, I will make the table here. This is the table. Okay, so the first row will always for the initial. The second for the change, and the last row is this is the equilibrium concentration. So first, let's put the givens that we have. So for the initial concentration of A, it was 2. The initial concentration of B, it was 3. We don't have initial concentration of C, so C is not there in the beginning, so we will consider C as 0. Okay, now what we have at equilibrium, we have only one information at equilibrium, which is the concentration of C, which is 2 molar. Now let's see how to use this table. Okay, so first we have the initial concentration of O. We need to determine the change, what will happen for this one. So we know that we started only with reactants. So these reactants, of course, will form a product. Okay, so the start will be forming the product, and we have a higher rate for the forward reaction. That's why this concentration of this one will decrease, and the concentration of C will start to increase. So at the beginning, to reach equilibrium, we need to produce a product. So we will decrease the concentration of reactant and increase the concentration of product. So this one, A or B, will be decreased, so the change will be a negative sign, so it will be decreasing. And the change of C is increasing, so it's a positive sign. Now we need to put a variable, and this variable will be using the coefficient. So for A, it's 1 mole, so the variable will be 1x. For B, it's also 1, so the variable will be 1x. For C, we have 2 coefficient of 2, so this will be 2x. So this is the change that will happen for these concentrations during the reaction. Now, when we adding these two, we will reach the equilibrium. So we will take the initial, add it to the change, and this will give us the equilibrium concentration. So it means for A, it's 2 minus x. For B, it's a 3 minus x. For C, it's 0 plus 2x. Okay, and some point you will have one at least given or other way. So if we have only one given, so we will use this one to determine the value of x. So we know that 2 of x is equal to 2. So I will solve it for x here. So 2 of x is equal to 2. It means x is equal to 1. So if x is equal to 1, so we will determine or substitute for the value for x here and find the concentration for A and B. So this one would be 2 minus 1, it's 1. For this one, 3 minus 1, so it's 2. So this will be the concentration, or this will be the concentration for A and B at equilibrium. Okay, so the concentration of A at equilibrium, it will be 1 molar, and the concentration of B at equilibrium will be 2 molar. Okay, let's have another one. Okay, so we have another reaction with 4 substances here. CO plus H2O will give CO2 plus H2. So what we have here, if we started with 1 mole of CO and H2, so 1 mole of each will be mixed in 2-liter flask. Okay, at equilibrium, we will reach number of moles of CO to be 0.5 moles. Calculate the concentration of all the substances at equilibrium and calculate the value for K. Okay, so first I will just write the given. See, we have moles here and we have liters and we have moles again. So we can do the ICE table with using moles. It's easy to do, but when you find the equilibrium, you'll find the equilibrium moles, number of moles at equilibrium. At this point, you can't use it for K or can you use it for concentration? You need at the end to divide it by the liters because we know that the molarity equals to moles over liters. But from the beginning, I will convert all the moles to molarity and using as the molarity. So the concentration of CO, which will be equal to the concentration of H2O because both have the same number of moles, which is 1 mole over the volume of the container, which is 2. This will be 0.5 molar. So this is the initial concentration for both. We have another given here, which is the concentration number of moles of CO at equilibrium. So we have 0.5 number of moles over 2. So this will be 0.25. So from the beginning, I convert all moles and to concentration to molarity and using as a molarity. Now I will start by putting the reaction. So H2O, so we get CO2 plus H2O. I will draw the table here. Okay, the first row is for the initial part, the second for the change, and the last one for the equilibrium concentration. Done. Okay, let's put what we have. We have the initial concentration for both H2O and CO, and this is 0.5. So I put 0.5. 0.5. What else? We have another information, the equilibrium concentration for CO, which is 0.25. Let's solve the Okay, so what we have here, we have the initial concentration for CO and H2. We don't have any information about CO2 and H2. It means he didn't start by adding CO2 and H2. So the product before the action, we have no product. So it will be 0 and 0. Okay, with time, so we have reactants. So these reactants will form a product. So the concentration of the reactant will decrease and the concentration of the product will increase. So this one will be a negative part and this one is a positive. Okay, so the change for the product for the reactant would be a negative because it's decreasing, and the change for the product will be positive because it's increasing. The variable again will be depending on the coefficient. So we have one coefficient here, so it will be 1x, one coefficient will be 1x, one coefficient 1x, and one coefficient 1x. And again, remember we said that when you're adding these two, it will give you the last row. So 0.5 minus x should be equal to this value. And this one, 0.5 minus x. This one is x and this one is x. Okay, we have something here. We can solve it for x and find the value for x, which is 0.5 minus x equal to 0.25. So 0.5 minus x equals to 0.25. We'll solve this one for x, and this will give us x 0.25. So this is the value for x. We have the value for x 0.5. So now we can substitute for the x or for the x in the other equations and find the concentration at equilibrium. So this one will be 0.25, 0.25, 0.5. And again, it's not necessary to all substances have the same concentration. No, they will be constant but not equal. But in this case, we're lucky because they are equal. So I will find the value for K. It would be products over reactants. We can substitute, and because they have the same value, so it will be 0.25 times 0.25 over 0.25 times 0.5 means it will be equals to 1. Okay, the last thing, we have another reaction here, Na2 plus 3H2, it will give 3, okay, this is 2, sorry, 2 NH3. Okay, if the initial pressure of Na2 and H2 is 4, so we have the initial pressure. So the initial pressure for Na2 is equal to the initial pressure for H2, and it's equal to 4 atm for atmospheric pressure. And at equilibrium, the total pressure, it's the meaning of total pressure. So it means we started the reaction with only reactant 2 Na2 and H2, and the pressure for each is 4. After reaching equilibrium, so the reaction will proceed and we will have equilibrium. So we will having N2, H2, and also product NH3. The pressure inside the containers of total one will be 6 atm. So it means the pressure for N2 plus the pressure of H2 plus the pressure for NH3 is equal to 6. This is at equilibrium. Okay, we need to calculate the pressure for all the substances and find the equilibrium of the value for K. Okay, so I will start by putting the equation here to write the ice. Why you need to use the ice again? Because we have the initial and we have only one formation at equilibrium, so we need to use the ratio between the coefficient in order to find the equilibrium pressure or the equilibrium concentration. And this one can be easily done by using the ice. So I, C, and this is the change, so E at equilibrium. Okay, let's find what we have. The given is was this one initial 4 and this one initial 4. Okay, so these are only the given here for the table. So we'll continue. For this one, we don't have any reactant and any product before the reaction starts, so it's 0. The change, again, we have only reactant, so it will form a product. So these reactants will decrease and the product will increase. So this will be a negative value and this will be a positive value. Now use the coefficient for n, and it's 1, so it will be 1 is x. For this one, it's 3, so it's 3x. For this one, it's 2, so it's 2x. The equilibrium, again, we will adding these two, we will reach to the equilibrium pressure. So it will be 4 minus x, 4 minus 3x, and 2x. Okay, we can solve it for x here because we don't have any value at equilibrium. So if you have a value for at equilibrium, we can solve it for x, but we don't have. So we need to use the other given here. So he told us that all the pressure at equilibrium equal to 6. It means if you adding the 4 minus s plus 4 minus 3s plus 2x, it will be equal to 6. So I'm going to add these. Equals to 6. Now I will solve for x, and you will find that 2x equals to 2, so x equals to 1. Okay, so the value for x will 1. Now we will find the pressure for each substance by substituting for x. It will be, this one will be 3, and this will be 1, and this one will be 2. So this is the pressure for each substance at equilibrium. So the pressure for Na2 is 3, pressure of H2 is 1, pressure for Na2 is 2. Now we need to find the Kp. So it will be the pressure of NH3 to the power of 2 over the pressure for Na2 times the pressure for H2 to the power of 3. I will substitute for these values. So for this one, it's 2 to the power of 2. For this one, it's 3. And for this one, it's 1 to the power of 3. So it means it will be 4 over 3, and this is the value for K.